This is a lesson on electric power in a unit on circuits. I wanted to start with a quick review of electric potential energy because that's where the energy comes from when we're talking about electric power, is electric potential energy. We know that there's energy associated with a charged object in an electric field, and that depends on the charge and the value of the voltage. All right, so we looked at that. If we're looking at a circuit and thinking about conservation of energy, we would actually have a change in electric potential energy, and that would equal Q delta V. We're also going to remember that we have a constant electric field, and in that constant electric field supplied by the DC voltage, we're going to have this potential difference, right? Whatever the EMF is, that's what we're talking about. We're going to remember that in a circuit, this DC voltage supply provides a constant potential difference and provides a constant electric field through which current can move, right? We need a potential difference in order for current to flow, and this is constant in the case of a voltage supply. So when we think about the electric power, the energy used in a circuit, we're thinking about an energy per unit time, right? That is what we covered in power and energy use in a long ago unit on work and energy, is power is the rate of energy use. So we're thinking about the rate of energy use in a circuit, and that's why I brought up the electric potential energy, because that's what a battery does. It provides this potential difference where the charges have an electric potential. So when we think about energy, we're going to think about Q delta V. Well, when I'm finding power, I'm going to use the whole circuit, so I need an N amount of charges, and I need to divide by the amount of time down here still, right, time. And what I'm going to notice, this term right here, Q over delta T, or an amount of charge over an amount of time, is a current. So now I can just pop in current into that equation, and you can see where power comes from then. Power is current multiplied by voltage. That voltage difference, remember that's a difference supplied by a power supply or over a circuit element. There's a voltage difference, but in these equations we just represent it with a letter V. So it's a little sloppy, but remember that concept is in there. And using V equals IR, Ohm's law, we can rearrange this into different versions of the same equation, and any of these is an equivalent use of this equation. I recommend using the version of it of the quantities that you have given in your circuit or can find in your circuit. I'm also going to note that they'll talk about like the energy supplied by a source, a voltage source, as opposed to the energy dissipated by a resistor. So if you're looking at just a resistor and they're saying what's the energy dissipated by a resistor, use the value of that resistor, whatever that is, whatever that resistor is, use that value. And the voltage drop is the voltage drop over just that resistor. You can't use the voltage on the whole circuit. You have to find the specific voltage over that resistor, or conversely, the specific current going through that resistor. Okay, so be careful when you're finding it for just a resistor. If you're looking at a total power supply, to me this is the situation where looking at an equivalent circuit is going to be more helpful. So find the equivalent resistance, and this current in here is going to be the current for the whole circuit, the equivalent current, and the equivalent resistance with the whole voltage supplied by this circuit. I picked out an example for us to look at these concepts and get a review of finding values for resistors in series as opposed to parallel. And you can see that there's series and parallel here. I borrowed this from Cutnell and Johnson, chapter 20, in the back of the chapter number 52. The sketches show 3 different resistors in 2 different circuits. The battery has a voltage of 25, so this is the same battery in both of these situations. The battery is 25, and the resistors have the values of 50, 25, and 10. So this is 50, this is 25, and this is 10. This is also 50, 25, and 10. It asks, for the circuit on the left, so the series here, determine the current through and the voltage across each resistor. So we want to find the current and the voltage. And then part B says repeat A for the circuit on the right. So we want to find the current through each resistor and the voltage on each resistor here. And then finally, we're going to integrate power, and we're going to look at the difference, determine the total power dissipated by each circuit. So they have the same voltage supply and the same resistors in it, but they're arranged differently. So we're going to see which circuit is delivering more power to those resistors, to the load of that circuit. So let's start with the series circuit over here. And I'm going to note that I can find our equivalent here. Our equivalent is very easy to find. I have 3 resistors in here and they add in series, so I'm just going to take them and add them. 50 plus 25 plus 10, well, that's 85 ohms. Okay, and this simplifies down to an equivalent circuit where there's just one resistor, and I could find the current through that. For a circuit in series, all of those elements have the same current. So I'll find the current, which is the current through the battery, which is I1, which is I2, which is I3. We could just call it I if you like. And using Ohm's law, I'm going to take the total voltage and divide by the total resistance. So that's 25 from the battery and 85 ohm. And when I find this I for this circuit, you take that, it's a little under a third, 0.2936. I rounded it off at 4, and we have current, so that'll be amps. So that's the current through all of the resistors in the circuit. We can easily find the voltage over all those resistors. I would say V1 equals IR1, so I would take that current, 25 over 85. And multiply by the resistor there, which is 50. So I get, when you do that, you get 14.7 volts. Okay, so of that 25, I'm losing 14.7 here, 14.7. I can keep going here. V2 is going to equal IR2, so I'm going to take the current and multiply by R2, which is 25, and I get half of this, 7.4-ish volts. V3 equals IR3, so same current multiply by R3, which is 10, and I'm going to get a fifth of this one, 2.9 volts. Okay, so those are the voltages over each. This will be 7.4, and then this will be 2.9 volts, and we've used up all of the 25. When you add all of that together, you should get 25 volts. Okay, the current through it is this value. So I'm going to go ahead while I'm here and calculate the power. All right, so part C for this circuit, the power. I know the equivalent resistance and I know the voltage. And so I'm going to use this last version of it, V squared over R. Power is V squared over R. I'm going to take the equivalent resistance and the total voltage on the whole circuit, and that will equal 25 squared divided by 85. And when I divide that, the power dissipated by this series circuit is going to be 7.353 watts. Okay, so very straightforward circuit to analyze. We didn't need any of these voltages of the individual resistors. If I wanted to find the power dissipated through each one of these resistors, I would use just the voltage over each one of these resistors. I would use just the current. So that may be the easiest way to do that, is to use IV if you wanted to find the power for each individual resistor, because you know the voltage over each and you know the total current. You could also use the V squared over R term, and that would give you equivalent power for just that one circuit element. You use the voltage through that element and the resistance on that element, or the current through that element. Just those values, not for the total circuit. Okay, so let's work on this other circuit over here. What I know for a parallel circuit is V equals V1 equals V2 equals V3. And I can just call that maybe V for the circuit, and that is 25 volts. All of these branches, because they're in parallel with one another will all have the same voltage, and so they're all 25. So that I answered part of that question for A, find the voltage across each resistor. I still need to find the current over each resistor. What I may do to do that is to just say like I1 equals V1 over R1. That's a pretty easy thing to do, and I can do that for each resistor. I2 is going to be V2 over R2, and all of these V's are actually the same voltage, 25. So I'll do 25 over 50 here, and 25 over 25 here, and 25 over 10 here. And so you can see that this last one is 2.5 amps. This is just 1 amp, and this is just half an amp. So this was a pretty easy circuit in order to figure out the voltage and the currents. I'm going to note that the current from the battery, when I add all of these up, right, when the current leaves the battery, I from the battery, it's going to go around, it's going to branch here, and then it's going to branch here, and it's also going to branch here. So that 1I battery is going to be all of these currents added together, and that's 4 amps. I can just add all those together. I could also find it by taking the total voltage and dividing by the total resistance in here, but I haven't found our equivalent. I haven't done that yet. I haven't found a need to. I haven't needed to yet. And so when I get down here, like for part C, I used the equivalent resistance on this circuit because it was something I knew and could easily calculate. But when I find the power for this circuit, I don't know the equivalent resistance, so I'm not going to use the middle version, and I'm not going to use the last version. I'll use the IV version. So IV. The current through the equivalent current through the total circuit here is going to be 4. And I'm going to multiply that by the voltage. The total voltage on the whole circuit is 25. And you can see the power over on this side is 100 watts. We are getting over 10 times the amount of power out of the second circuit than we are the first circuit. This circuit up here is how the circuits in your house work. When you plug things into the wall, when you plug devices, when you apply load, when you apply resistance, by plugging something into the wall and closing that circuit, all of those are connected in parallel. So R1 might be your oven, and R2 might be your refrigerator, and R3 might be your coffee maker, okay? So when you plug those in, they're all going to get the same voltage. That's what we need, is all of them get the same voltage. And they'll each get a different current, and the circuit breaker will work when this current gets too large in here, right? This voltage will be the same the whole entire time, but as you load more and more devices onto the circuit, the current's going to keep going up and up and up, okay? So that will increase the power through your circuit, but the current will get too high, and that is a hazard to have too high of a current. So that's why they put circuit breakers on a circuit like this, is because you don't want the current going too high. It makes sense to add things in series. I'll just add something onto the circuit, but mindfully you can see that you're not going to get as much current going through each element. You might not get the current you need in order to create the heat in the oven you need, or to run your coffee maker, or to run the compressor in your refrigerator. All right, so that's why you connect in parallel rather than series when you're doing circuits in your house.